Welcome back, guys. In this video, we'll do another example of the first derivative test. This one involves an exponential function. Now again, if you've already got the idea, you don't have to watch all of these videos. I just wanted to do one example of all the types of functions that you're likely to see in your homework and on your quizzes. But if you have the idea, this is not, you don't have to watch all of these. It's not necessary. Okay. So these are the questions. You might be asked to find the open intervals where the function is increasing or decreasing. You might be asked to use the first derivative test to find and classify relative extrema, and then use that information to graph the function. So to find the open intervals where f is increasing or decreasing, we're going to do the same thing that we always do. We start by finding the domain of the function. And remember those three things that we need to rule out. We don't want to divide by 0. We don't want to take square roots of negative numbers, or fourth roots or sixth root, or any even root of a negative number. And we don't want to take a logarithm of a negative number or 0. But there's no division here. If you're saying to yourself, oh, but Miss Townsend, what about that negative exponent? You're right. You're absolutely right. We could write that as 1 over 3 to the x. You could write it this way. But there's no division by 0 because 3 to the x looks like this, guys. That's never 0. Never 0. It does not matter what x is. If x is negative a million, it's going to get close to 0, but that's really a 1 over 3 to the 1 millionth, which is a really, really tiny positive number. So, yeah, we're not dividing by 0 there. There are no even roots, and there are no logarithms. So the domain is all real numbers. You can write it like that, or you can write it like that. Then after you find the domain, in order to find these intervals where the function's increasing or decreasing, we need to find the endpoints of those intervals where f prime is positive or negative. So we need to find out where f prime is equal to 0 or where f prime is undefined. So those are the critical points. So after finding the domain, we find the critical points of the function. And we're going to use the product rule because I've got two functions of x multiplying each other. So according to the product rule, we take the derivative of the first function and then we multiply by the second function. And then we add the derivative of the second function. Whoops. Sorry. Times the first function, undifferentiated. And then you just compute those two derivatives. Derivative of x is, of course, 1. And the derivative of 3 to some power, derivative of a to the x, this is not a rule that we have emphasized a lot very much. The derivative of a to the x is a to the x, so exactly the same exponential, times natural log of the base. So the derivative of 3 to the negative x, well, it's this rule, but notice you've got a negative x inside. So we've got an inside function, we'll have to use the chain rule as well. So according to the chain rule, we have to do the derivative of the outside first. Derivative of 3 to some power is 3 to that power. So you write down the same exponential, multiply by natural log of the base, and then you multiply by the derivative of the inside by the chain rule. And then you multiply that by that x over there from the product rule. Derivative of negative x is negative 1, and so we get this. We've got 3 to the negative x minus, and I'll pull the x out, x times 3 to the negative x times natural log of 3. I'm bringing that minus out front. And I have this now. Now remember, when you're finding critical points, you always have to compute the derivative and set it equal to 0 and solve for x. So f prime of x equal to 0. This almost always requires factoring if the expression that we have here factors. And this one does factor. I can factor out that 3 to the negative x because I'm looking at this as a term and this as a term, and they both have the 3 to the negative x in common. So you get that out, and then you say to yourself, 3 to the negative x times what gives us the first term? That's just a 1. And 3 to the negative x times what gives us the second term? I need the negative x and the natural log of 3. Natural log of 3 is just a constant. I know it looks weird, but it's just a constant. It's just like a 3. It's just like a number. It's a number times x. Okay, so this is f prime. It's been factored, and we're setting f prime equal to 0 and solving for x. Now, this exponential is never 0. You might not remember this from pre-calculus, but 3 to the negative x is actually a decreasing exponential function. It looks like this. Replacing, if it was just 3 to the positive x, it goes this way. If you replace x with negative x, it's a reflection across the y-axis, decreases instead. But notice the y values on that graph never cross the x-axis. What does that mean? The y values are never 0 because these are all positive y values up here. Y equals 0 is right here, and the negative y values are down there. But y is never equal to 0 on an exponential. So the only way that this times this equals 0 is if this factor equals 0. So we've got 1 minus x times natural log of 3 equals 0. So we can add this to both sides, and then divide by natural log of 3 to get x by itself. And we get x equals 1 over natural log of 3. So that is our critical value. Okay. I don't know what that is exactly, but I've got a calculator and I can find a numerical approximation. It's just a number. Just a number, a little positive number. Okay. So it says find the critical values by taking the derivative, setting it equal to 0, and solving for x. Also, go back here and think about whether if there's ever an x value where this is undefined. There isn't. Remember that negative exponent can be brought to the denominator. So this is 1 minus x times natural log of 3, which is just a number, all divided by, if I bring that 3 to the negative x to the denominator, that's going to make it 3 to the positive x. That's never 0. The numerator is basically a polynomial. It's a linear polynomial because natural log of 3 is just a number. It's just a number times x times plus 1. So this is well defined for all x. So that is our one and only critical point. So we need to consider x values in the domain, which happen to be all real numbers, for which f prime is undefined. And this time, it wasn't undefined. There's no x values that would cause it to be undefined. Okay. So now we want to find let's answer the questions that they asked us. We want to find the open intervals where the function is increasing or decreasing. In order to do that, we make a sign chart, put our critical value on the number line, and I like to put all of the factors of f of x over here below the number line. I think I'm going to use this version of it. 3 to the x is one factor, it's in the denominator, and 1 minus x times natural log of 3 is in the numerator. So I've got a number divided by a number. The signs of those numbers determine the sign of f prime. And remember, f prime is 0 right here. So you have a 0 slope at that x value. Well, 3 to the x. Again, because of the graph of 3 to the x, because of the way exponential functions behave, I know that that's always positive. It doesn't matter what x is, that's positive. And then down here, if I want to figure out what happens to this, to the left and right of 1 over natural log of 3, I need to find out what 1 over natural log of 3 is and find numbers to the left and right of that number. Just need a numerical approximation. So I've got 1 divided by natural log of 3, close parentheses. It's about 0.9, approximately 0.9. So I can substitute an x equals 0 on this side and x equals 1 on that side. That'd be great. At x equals 0, we have 1 minus 0, which is 1. So f prime is a positive divided by a positive. A positive divided by a positive is positive. And then over here at x equals 1, we're going to have 1 minus natural log of 3. That's negative. So I have a negative divided by a positive, which is negative. So the first question said, determine the open intervals where the function is increasing and decreasing. Once you've created your sign chart, you're almost there. If the derivative is positive, the function is increasing. When the derivative is negative, means all of our slopes are negative, the function is decreasing. So let's answer that first question. And it's on an interval from this x value to this x value. So you're reading it from left to right. It's increasing from negative infinity to 1 over natural log of 3. And the function is decreasing from 1 over natural log of 3 to infinity. Okay. Now the second question said, use the first derivative test to find and classify the relative extrema. Say, well, here's my critical point. Does f prime change signs there? It sure does. Do I have a max or a min? You can see just looking at the arrows that we're going to have a max there. The function goes from increasing to having a 0 slope to decreasing. So we're going to have a relative max at the top. So we'll say f of 1 over natural log of 3, which is x times 3 to the x, and my x is 1 over natural log of 3, and this is 1 over natural log of 3. That is my y value on that. That's kind of odd looking. Okay. And that is a relative max. And let's get a decimal approximation for that. We've got 1 over natural log of 3 times 3 raised to the negative, open parentheses, 1 divided by natural log of 3. Close parentheses for the natural log, close parentheses for the exponent. And we get about 0.335. It's not the exact answer, that's exact, but this gives me a better sense of what's going on. And this is about 0.9. So at about 0.9, the y value is about 0.335. Okay. This is a relative max by the first derivative test. Okay, and now we'd like to graph the function. With the little information that we have so far, we'd like to have some sense of what the graph looks like. Well, we know it's well defined for all real numbers, and at x equals 0.9 approximately, y is equal to that, and that's a relative max. So I'm just going to write 1 over natural log of 3, and this is about, that's about 1, and if that's about 1, this is supposed to be about 1/3, a little bit more than that. Okay. Well, I got 1 point on the graph. What else do we know? We know the function is increasing on the interval from negative infinity to that number, and it's decreasing over here. What else do we know? Well, our function looked like this. It was x times 3 to the negative x, or we could rewrite it this way, x over 3 to the x. Now 3 to the x is exponential. That grows much, much faster than x. So as x goes to infinity, we'll see later that this quotient approaches 0. We're going to use something called L'Hopital's rule, which we're going to learn in the next couple of weeks, to show that that goes to 0. When x is positive, is a positive over a tiny, or x is positive, we get a positive number over a positive number. So we get something that's approaching 0 from the positive side. When x is negative, I've got a negative over a positive, so it's approaching 0 from the negative side. When x is 0, of course, we get 0 here. So well, it's kind of like that, but that looks like it has a min somewhere, but it doesn't. So it's increasing the entire time over here on this interval. It has a max at that point, and then it's decreasing over there. Now there's got to be more information about how this function's changing. If it's increasing, I mean, it could increase like that, or it could increase like that. Those are two very different shapes, and we're going to figure out which of those two shapes it is in the next section. Okay, but for right now, we're able to find a relative max and the fact that it's increasing on that side and decreasing on that side.